All right, well, welcome back for our next unit. This unit that we're starting right now actually is one of the most central and feared units in all of the Chem 1 classes. This is the unit that's based on something called stoichiometry, which is basically the idea of using balanced chemical equations to be able to predict amounts of products or amounts of reactants that you need. So this is kind of something we'll be building to over the next couple of lessons. So we're starting here with something pretty basic, which is the concept of mole-to-mole ratios. And then over the course of the next couple of lessons, we'll be moving towards it. So you want to make sure that you've got a calculator, maybe a periodic table, some scratch paper, something along those lines. Because again, to have these videos be effective for you, it's more important that you're actually active as well as just sitting there on your couch eating your snacks. So make sure that you're ready for this. So anyway, what we're going to take a look at today is the concept that we can use chemical equations like a recipe. I'm assuming you've made things before at your house where you have to literally follow directions. I know something you're not great at, but that idea of some of this plus some of this and then you get this much product to it is kind of what we're doing. So really chemistry and recipes are basically the same thing. So except don't lick the spoon, right? So let's take a look at the example that we're going to use. I hope you're not too hungry because we're going to be talking about cheeseburgers a lot in the course of this. I use it as one of my teaching examples. God, I'm hungry. Look at that burger. That thing's a piece of art. So anyway, let's say you're going to invite some friends over and you need to make some burgers to your friends, for your friends, and you kind of know what the basic hamburger recipe is. But let's say you've got a bunch of friends coming over and you know you need to go to the store rather than just yelling, "Ma, go get me some burger stuff." You need to come up with an actual list of ingredients. How many burger patties do I need? How many buns do I need? How many pickles do I need? So you got to kind of start doing a little bit of math. And this little bit of math that we're going to do here is just like the math we do in chemistry. It just happens to be a little bit easier to understand. We're talking about pickles and burgers than we were talking about like magnesium and sodium and stuff. So we're going to use our burger friend here. I chose to go with a less exotic burger, even though that one on the previous page looks so much more delicious. I'm going to go with this basic one just because the math on it's a little bit easier for us to deal with. So this is the basic cheeseburger that we're going to use. It's actually a double cheeseburger because those are pretty small patties. So this is an image I stole from a fast food website. So sorry. Anyway, critical ingredients you have for a little double cheeseburger like this. You have to have a bun. You have to have 2 meat patties for it to be a double cheeseburger. Got to have 2 cheese slices. Now, I'm from Wisconsin. That's not enough. But for the purposes of what we're doing here, we're going to call it 2 cheese slices. And then for the last part of our recipe, we'll have 3 little dill pickle slices on top. And those 4 things, all combined together makes one single double cheeseburger. So this is the idea of the recipe that we're going to use for the basic of this. So we've got a ratio of stuff, right? Bun, meat, cheese, pickles, and then we have the end product, our compound, I guess, is a double cheeseburger. So in order to make this kind of more relevant to our chemistry lesson, I'm going to make this look more like a chemical equation, just to kind of, back away from, yeah, I know I need a bun and I know I need a couple burgers. What does it look like? So we're going to call a bun a B2. Buns are diatomic. There's a top half and a bottom half, so you know I'm right. So we'll have the B2 for the bun. We'll have 2 meat patties, which is just we'll use the letter M for our meat patties. We'll use the element C for cheese in this case. I guess I could use CH, and then we'll use P for pickle slices. So we'll need 2 meat patties, 2 cheese slices, 3 pickles. And so you can see down below is we've got this rather large looking yellowish thing, which is kind of our chemical equation for a cheeseburger, double cheeseburger. We need 1 diatomic bun, we need 2 meat patties, we need 2 cheese slices, and 3 pickle slices. Those are our reactants. And this should be an arrow, but anyway. Then we have this thing. I know it looks really crazy to write that. Why didn't I just write cheeseburger? Well, because remember, in chemistry, law of conservation of matter, a cheeseburger really is the sum of its parts. So I wrote this out as the sum of its parts. There's the top bun, and then there's the 3 pickles, and then there's a cheese slice, and then a piece of meat, and then a cheese slice, and then another piece of meat, and then the bottom bun. So that's really is the formula for what a cheeseburger would look like. Kind of looks like organic chemistry to me. But that's the basic reaction that we're going to use for kind of the remainder today. So a diatomic bun plus 2M plus 2C plus 3P yields one thing here that we're just going to call cheeseburger, double cheeseburger. Okay, so keep in mind that as we're doing our chemical equations here and we're doing our reactions, it's really important that we balance our equations. This is something we sort of take for granted in recipes because when recipes are presented to you, they're already balanced. So when you make say chocolate chip cookies, you don't just say throw together, we need flour plus butter plus sugar makes cookies. You always say certain quantities are associated, 2 cups of flour plus 1 cup of butter plus whatever else is going on in there. We always put those things in there. So in a chemical equation, though, that you're making, you may have to take that step. So if you take a look at these two burgers here side by side, they're definitely not the same burger. They have the exact same ingredients, but the one on the right is kind of the basic single burger, and the one on the left is the burger that we're trying to construct. So they have different balanced equations to them, and it's important to do this because this gives us the ratio, this gives us the actual products that we want to create. And if we want to make BP3CMCMB, a double cheeseburger, we have to have all of those ingredients represented accurately in our reactant. So make sure that you're balancing your equations. Again, the coefficients give us the reaction that we're talking about, not just the names of the products in the reactant. So don't forget to balance your equations. Okay. What can we get from a balanced equation? What can we get from a recipe, right? There's a couple of different things that we know from a recipe. Number one, we know the identity of the reactants. We know it's flour, butter, and sugar, or we know that it's buns and meats and cheese. Plus, we also know the quantities that we need, the ratios of the things that are involved. And what's really important then for our balanced equation is that this balancing part, the coefficients, is what actually tells us the ratio. How much of each do we need? Because 1 bun plus 8 burger patties isn't going to make us the cheeseburger that we want. So we want to be really specific about that ratio. And it turns out that that ratio then, those coefficients, are actually a conversion factor. And we don't think of it as that way, but it's a conversion factor just as much as 12 inches equals 1 foot or 3 feet equals a yard. In this case, our conversion factor is 1 bun goes with 1 cheese. Oh, I have this wrong. Buns and cheese are not in a 1-to-3 ratio. Buns and cheese are in a 1-to-2 ratio. Meat and pickles are in a 2-to-3 ratio. For every 2 meat patties, I need to have 3 pickles. So if I have a burger there and I know there's 2 patties, I know there's going to be 6 pickles. It's a way that we can kind of do that scaling of our recipe in terms of figuring out what's what. Our cheese and meat are in equal proportions. They're 1-to-1, or we could say 2-to-2 because it's a double cheeseburger. But for every patty, I need 1 piece of cheese. So this is a kind of a way of doing our scaling up. If I'm looking around like I've got a pile of burger patties, how many burgers can I make? We can use that ratio to kind of help us predict how many burgers we can make or how many pieces of cheese we need or how many pickles we need. So in terms of this idea of scaling recipes, you guys know what it's like. I'm going to make a double cheeseburger, and then like 7 of your friends show up. Like, well, damn, what do I need to do now? Well, now you need to worry about scaling up that recipe. How much of everything do I actually need? And this is kind of how I started that idea. You need to scale up your recipe, sort of multiply it out, in order to be able to make sure that you've got enough of the reactants and you're going to make enough of the products. So we're starting here with the concept of I need 7 products. I need 7 full cheeseburgers. How much of the other things do I need to actually make this whole process work? So this is kind of that idea of going to the store. So here's my reaction. Again, my diatomic bun, my 2 meat patties, my 2 cheese slices, my 3 pickle slices. I need to make 7 of that set. So what does this look like? Well, I just kind of multiply it across, right? If it's still a ratio, I can just multiply all of my coefficients by 7. That's that idea of scaling. I'm going to show you a different way to do this that works with kind of funkier numbers in a little bit, but this is the basic idea. Scaling it up. I'm multiplying it by some number to give me the ratios of things that I need while maintaining the ratio. If you take a look in here, the 7 to 14 to 14 to 21 to 7, if I reduce that down, it's still the exact same ratio. I haven't changed anything. It's still 1 of these to 2 of those to 2 of those to 3 of those makes 1 burger at the end. It's still the same ratio, just scaled up or potentially scaled down. So scaling down, kind of the same idea. I don't know why anybody would ever want to make a third of a burger, but let's say you're making little burger sliders or little snacks, hors d'oeuvres, right, that you're making those for your friends. And I only need to make 1 burger and I need to make thirds of burgers or something along those lines. It's kind of weird, but the same process works. Don't freak out just because the multiplier is a less easy number. So again, with this one, if I'm trying to make third burgers, which is kind of really weird, but if I were, all I would do is multiply that 1/3 across my entire set of coefficients, and you get something like this. Again, it looks really weird. For each of my hors d'oeuvres, I need 1/3 of a bun, 2/3 meat patties, because remember there's 2 patties, 1/3 each, 2/3 of a cheese slice, and 1 single pickle. Be kind of a lame hors d'oeuvre, just a bite, but anyway. And that would give me a 1/3 little mini burger, kind of an hors d'oeuvre size bite. So again, that idea of scaling up, scaling down is really what we're aiming at, not just why would somebody make that many burgers? But that idea of simply taking the ratio that you've got, in this case a 1 to 2 to 2 to 3 makes 1 product, and scaling it by some sort of a multiplier, either dividing it by 3 in this case or multiplying it by 1/3, multiplying it by 7, multiply it by 100, multiply it by 1,000. It doesn't really matter what we're doing. This idea of scaling doesn't change the ratio that's in the bottom. The ratio comes from the balanced chemical equation. Okay. So, what if I have something really bizarre? Like a whole bunch of people are coming over. I got to feed the entire class, like when I make waffles for you guys. Now I have to scale it up quite a bit further. And trying to do this by hand, simply multiplying it across, sometimes gets a little inconvenient. So, I'm going to go back to Zerfunde-Fraction. Yeah, you knew it was coming. I'm going to go back to this idea of using dimensional analysis and using conversion factors, because in the end, it's actually faster. I know sometimes it's a little bit harder to understand what you're doing or why you're doing it, so let's focus on the skills that you're doing. That balanced equation is a conversion factor. I know for every one bun, I need 2 pieces of meat. One bun equals 2 meat patties. One bun equals 3 pickle slices. It doesn't really matter how I start or how I end. That essential ratio is still the same, and that's what we're going to go with on this one. So here's our balanced equation again. These coefficients, and again, it's a 1 in front of the bun, 2, and a 2, and a 3, plus a 1 in front of the burger, that becomes our conversion factors. And we're going to be able to use those just like we'd use a conversion factor of 12 inches equals a foot in a dimensional analysis problem. So here's our couple of sorry, I didn't mean to go past that so fast, but 1 bun equals 2 cheese, 3 pickles. Again, it doesn't matter which one we're using, those equal 1 burger. Any of those pieces is a conversion that we're going to use. So here's what it looks like. Let's say I need to make 19, I've got 19 hamburger buns. How many burgers can I make? Okay, well that's an easy one. But how many slices of cheese do I need to use up all of those buns exactly? And then how many pickles would I need? I know you guys can do the math on this, but let's set up the example using dimensional analysis so that when we're doing it with chemical reactions, it makes more sense. So, 19 hamburger buns. I'm going to start there. There's my balanced equation. This is what it looks like as dimensional analysis. Start with what you're given. I'm given 19 hamburger buns, 19 B2s, right? And this is my conversion. My conversion is 1 bun needs 2 pieces of cheese to make a complete burger. Now I'm only focusing on the cheese here. Yeah, there's meat and yeah, there's pickles and all that other stuff, but I'm only focusing on the conversion from buns to cheese. One thing at a time, let's just do that piece. And because this is dimensional analysis, now I can just math it out. Multiply across the top, divide by anything on the bottom, and this gives me the really easy calculation. I know I need 38 slices of cheese to make this work. All right, how many pickles do I need? Second problem. Each time you do a conversion, use a separate problem for it in this case. So I'll set up my other one. I'm going to start with the same bit. Still start off with 19 buns. And now I'm going to use a different conversion. See how I crossed down the buns because I'm converting from buns to pickles. And the one that you're, it sounds stupid to say this, the one that you're trying to cancel out goes on the bottom. The one that you're trying to go to, which in this case is pickles, goes on the top. And then these numbers, the 1 and the 3, came from the balanced equation. That's my ratio. That's my conversion factor. 1 bun from my chemical equation is associated with 3 pickles, or it reacts with 3 pickles. And again, now it's a matter of doing the math. Multiply across the top, divide by the bottom, means I need 57 pickles. So again, this step of using this dimensional analysis will save you time in the long run. I know for these kinds of burger problems, not so necessary. I'm going to throw some chemistry at you here, and it makes it a little bit easier to do the math on that. All right, so when we're doing this, big idea, again, huge idea here, is that you have to have a balanced chemical equation for a reaction, and those coefficients in the balanced chemical equation are the ratios. It gives you the conversion factor to go from any one chemical to any other chemical. It could be reactant to reactant, product to product, reactant to product, anywhere in there. That's your conversion factor when you're setting up dimensional analysis problems. So here's a math one. We actually did this in the lab where we took a piece of magnesium and we combusted it. We burned it. Not truly combustion, right? But we burned it to make magnesium oxide. So there's my balanced equation. I've got 2 reactants. I need 2 of these guys to react with 1 diatomic oxygen molecule, and I'll make 2 of these MgO molecules. So when I start to do this in terms of a dimensional analysis problem, here's what it looks like as chemistry. How much oxygen would I need? How many oxygen molecules would I need to react with 10 molecules of magnesium? So if I put 10 molecules of magnesium in, super microscopic quantity, how much oxygen would I need to do to make this reaction happen completely with nothing left over? So here's what it looks like as a dimensional analysis problem. Again, I start with what I was given in the problem, 10 molecules of magnesium. Then I'm going to use my conversion factor. And again, this conversion factor is the mole to mole ratio, or the molecule to molecule ratio, comes from my balanced equation. 2 of these, 2 magnesiums, reacts with 1 oxygen molecule, and that's what we've got right here. And this tells us that we need to divide by 2. So it's multiply across the top, divide by the bottom, and we end up knowing that, oh, I need 5 molecules of oxygen. I know it's kind of obvious to look at it. I promise, invest the time now to learn how to do the dimensional analysis because these problems get more complicated. So start with the easy ones, practice the skill, so when it gets harder, you've already got the skill. We can also change this conversation now, instead of being about molecules to being about moles. And this is what we're going to do for pretty much the rest of the time here. It doesn't do us any good to have 10 molecules of magnesium. You wouldn't be able to see it. 10 moles of magnesium is actually a fairly substantial quantity of magnesium, and that's what we're going to use here. So it's the same exact concept, because when we're dealing with chemical equations, molecule to molecule works, but more importantly for us as big, huge creatures, moles to moles works as well. So all I did in this equation here is I changed the numbers from molecules to moles. If I had 10 moles of magnesium, it would still react in a 2-to-1 ratio. And then now my answer, instead of being 5 molecules, it's going to be 5 moles of oxygen that's needed. And now you can kind of guess where we're going in the future. We're going to be using molar mass to convert from moles to grams. It's coming next anyway. So here's your chance. How much magnesium oxide could we produce from 0.135 moles of oxygen? A little bit less obvious numbers here, so it's a little harder to do this one in your head. So this is a good time to practice. Can you set up a little micro-dimensional analysis problem, little mini wonder fraction, to kind of take care of this problem? So hit pause now, scratch it out. I'm going to do it right here next. All right, key with setting up dimensional analysis, right? Start with what you know. That 0.135 moles of oxygen needs to go on my top left square. There it is. And now what do I need to convert it to? I get that from the problem. I'm going from oxygen, where I'm starting, and I need to end with magnesium oxide. So that's how I've picked these two compounds to put in here. I've got oxygen, it goes down to cancel out, and I'm going to put magnesium oxide on the top because that's what I want, because that's what the problem asked for. And these numbers right here, the 1 and the 2, came from the balanced equation. There's a coefficient of 1 in front of the oxygen, and there's a coefficient of 2 in front of the MgO. So that's where these two bits come from. Again, those are our mole to mole ratios from our balanced equation. So again, math it out. It's 0.135 times 2, because you multiply across the top, and then you divide by 1. So our final answer here is 0.270 moles of magnesium oxide would be produced. Okay, so here it is for you. Practice for you guys. You've got an equation here. I'll pop the equation up here for just a second. If you want some challenge, see if you can write it out. But you're going to burn 3.5 moles of C2H6, something called ethane. How much oxygen gas do you need? And then a second problem, this is not done in one problem, 2 problems. How much CO2 will you produce? So again, if you're good at this, you can try writing the equation out. Hit pause, and you can kind of wait and move on. I'm gonna do it right here. You ready? Ready? Okay, so here's the reaction. It's kind of a tough one, actually. So if you got this written in balance, you did a really good job. This is a combustion reaction. So here's our ethane going in, our C2H6. Any combustion reaction reacts with O2. Our two products are always CO2 and H2O. And this is kind of a wicked one to try to balance out. So there's the balanced chemical formula on their balanced chemical equations. All right, so if you got stuck there, now you can hit pause again, and now you do your dimensional analysis. So again, we're starting with 3.5 moles of this stuff. And in your first problem, we're trying to find oxygen gas. How much oxygen gas do you need? So I'm going to convert from this stuff to the stuff right next to it, O2. So here's mine. 3.5 moles of C2H6. I'm going to cross the C2H6 down, and I'm going to put O2 on the top because that's the ratio that I'm looking at, C2H6 to O2. And again, my numbers right here, those are my coefficients, my conversion from my balanced chemical equation. 2 moles of C2H6 reacts with 7 moles of O2. Now it's just a matter of mathing it out. Multiply across the top, divide by the bottom, so that's 3.5 times 7 divided by 2 gets me 12.25 moles of O2. I think sig figs it should be 12 would be the correct answer if we rounded it to sig figs. Okay, next one. You didn't do this one. Now's the time to hit pause. Do the CO2 problem on your own. Come on, you can do it. Right? No. Okay. So here's the other one. 3.5 moles of C2H6. Again, I'm starting with what I was given in the problem, crossing it down in the next step, and then on the top, I'm going to convert it to what I want. I had C2H6. I want to know how much CO2, because that's the problem that was asked. How much CO2 will you produce? And then these numbers in front come from my balanced equation. 2 moles of C2H6 is going to produce 4 moles of CO2. I could have asked a question about water as well. We would have used 6 for that one if we wanted to. It doesn't matter which 2 chemicals we're using. Last thing, math it out. 3.5 times 4 divided by 2, because 2 is on the bottom, and we get 7.0 moles of CO2 are produced as a result of that. So hopefully you had some success with that particular process. All right, so what are we doing here? Balanced chemical equations is our recipe. So we need to know a variety of things from our balanced chemical equations. Like number 1, have to balance it. It can't just be buns plus cheese plus meat, because you could get a different burger, right? You got to have the exact right ratio to get the burger that you want, or in this case to actually get the chemical reaction that you want to make it correct and actually accurate mathematically speaking. It tells us balanced chemical equations tell us about what the names of the reactants are in products and kind of how many of each are involved, kind of who goes in, who comes out. And then most importantly for us, us, the most important piece, is that it tells us some ratios. We can think about it at a molecular level, how many molecules or atoms go in and come out, but more important for us is how many moles of things are reacting with each other. It's kind of our case quantity. It gives us that quantities that are visible to us on the macroscopic scale that we can deal with. So we're going to call them mole to mole ratios, although they are also atom to atom or molecule to molecule ratios. Next thing is that we're going to practice using the dimensional analysis, the Wunderfractions, yeah, to make sure that we're solving these mole to mole problems. Again, it doesn't necessarily seem like you need to do it here, but we're going to build onto this central step, and our Wunderfractions kind of get wider as we go. So it's kind of key to practice this with these easy ones. This works for things where the numbers aren't obvious or where you have complicated formulas. You can use this dimensional analysis between any two things in a chemical formula. It does not matter which two, both on the reactant side, both on the product side, one on each side. It does not matter, so it's kind of flexible in that sense, and it's easier to do that. And again, this step that we're using here is going to be the central step to more complicated problems that we'll be doing in future units. So there you go. I hope you're not too hungry from looking at all of those cheeseburgers. The next one doesn't have grilled cheese in it. It's the one after that. So you got a little bit of time. So make sure to go get yourself a snack. Next lesson is all about stoichiometry. Yikes, right? Some Wunderfractions.